We're going to look at the Bohr model in this video. I'm guessing that you probably kind of know the Bohr model. Maybe you didn't call it the Bohr model, but it's just this picture of an atom as having these rings or shells or energy levels around the outside, and that's where the electrons are found. Now, to be honest with you, I kind of starting now and moving forward, the nucleus kind of is what it is. It's got the protons and the neutrons, and it's in the middle of the atom, and I really have no problems with the nucleus. It's a pretty accurate model. It's pretty simple. But eventually we want to clean up the electron structure a little bit. That I've been told electrons exist in these little rings or shells and they fly around in circles. But do they really? And I think from here on out till the end of this unit, we really focus mostly on electron structure, because eventually when atoms interact with each other and they want to bond or do a chemical reaction, it always involves the electrons. The nucleus is involved in a nuclear change, but we can't do that in our lab. But we can certainly change the electron structure of a particular substance. So that's kind of where we want to focus our energies for the next, I don't know, week or so. And so this Bohr model really is just this model where the electrons are moving in circular orbits around the nucleus, and maybe you've kind of said that they're low energy and high energy. That, like, again, if this is my nucleus and there's these rings or shells or energy levels, that the energy level close to the nucleus is low energy. And as you move farther away from the nucleus, the energy levels get bigger and higher in energy. Higher energy. And so you may have like done models with M&Ms or whatever in another science class, or sometimes they take like licorice and they make rings around the outside of the nucleus and they put their M&Ms in the rings. Kind of, I guess. A couple things that are interesting. We did kind of mention that electrons can move. So just because you're an electron and energy level, like, I don't know, 1, it doesn't mean that I'm in energy level 1 for life. An electron can move or transition from one energy level to another, but it cannot exist in between energy levels. So you're in level 1, 2, 3. There's no like energy level 1.5. That you've got to be in a specific energy level. And to move from one level to another, an electron must gain or lose the exact, like, perfect amount of energy. So if you're trying to move up the energy levels, you can't go to energy level 2 until you have exactly that amount of energy. There is no such thing as like halvesies, like, I'm not quite there yet. Well, then you're stuck in energy level 1 until you have the exact amount of energy to get you from 1 to 2. We use the word quantum or quantized. We say like the energy of an atom is quantized, which just means like a quantum is a specific amount of energy required to move an electron from one level to another. Okay, so kind of like in this picture, there's this girl that's moving up the stairs, and in order to get from one stair to the next stair, she has to like step an exact amount. I mean, if she steps too short, she's just going to fall back down to the previous step. And so it's kind of like a quantum where each step represents a specific amount of energy. And you can't go from step 1 to step 2 unless you add in the perfect amount of energy. And now this is as opposed to continuous energy, where like this guy is just walking up a ramp, and he could take a small step, he could take a large step. He's continuously moving up the ramp. Oh. Where he's going to move no matter how much energy or how big his steps are. It's a little bit different with the atom. That the atom has energy levels that are quantized, more like a staircase. That, I mean, if she doesn't step high enough, she falls on her face and goes back down to the previous level. That you have to have the specific amount of energy required for each energy level, otherwise you're stuck in the previous level. Interesting. All right, so this picture is just chock full of good stuff. explaining emission spectra. So we mentioned earlier that the emission spectra is the specific colors of light that are released from these energized electrons of a particular element. Bohr's model predicted the specific frequencies or energies of light of the atomic emission spectrum of hydrogen. Each line of the specific has a specific frequency in the spectrum or a specific energy level, and that corresponds to a specific electron transition. All right, so let's try to figure this out a little bit. Here's some cool pictures. So first, just the general Bohr model. So the Bohr model's got the nucleus, it's got the electrons flying around in these rings, shells, energy levels, whatever you want to call them. If we're referring to hydrogen, there's a nucleus, and the nucleus is usually just one proton. Certain isotopes of hydrogen may have an electron, but it's usually just, a neutron. Usually hydrogen is just one proton, and then its corresponding one electron. Isotopes may have a neutron or two. Okay, so here's kind of a general hydrogen atom. Now, some very important vocab. We should highlight these guys or somehow make note of these. Ground state and excited state. Those are important. Okay, so the ground state is like home base. The ground state is the lowest energy level. It's like where the electron would normally be found. Now, one misconception is that it doesn't have to always be energy level 1. Now, obviously, with hydrogen, and there being only one electron, that one electron is going to be in the lowest energy level, level 1. Now, bigger atoms are going to have electrons in multiple energy levels. So if I'm like a big atom like xenon with 54 electrons, those electrons are going to be distributed amongst multiple energy levels. So for a particular electron, ground state might be level 2, 3, 4. It's just the energy level where that particular electron is normally found, as opposed to the excited state. So the excited state is once that electron has gained energy and jumped to a higher energy level. So here it looks like maybe we added some light. Maybe it was red light. So red light went in, and that excites the electron. So the electron then jumped up to a higher energy level. But high energy is always unstable. We should mark that in here. This excited state is not stable. Ooh. Electrons do not want to be in higher energy levels. They want to get back down to their ground state. But I can't go back to energy level 1 if I have all this extra energy. So we have to release that energy in the form of light. And so if it was like a red light that was added to the atom, so red light in, well then in order to go back down to the ground state, all that red light will be emitted. So the amount of energy level absorbed has to be the same as the amount of energy level released, so that I can get back down to my ground state. We mentioned then these spectral lines, the emission spectral lines. Hydrogen atoms absorb or emit light with an energy exactly equal to the energy difference between energy levels in the atom. So it may be in this particular case we moved from energy level, well I guess like in this first picture here, I don't know, it's kind of like an energy level 1. Then it jumped up to energy level 2. So if I want to go back down to energy level 1, I've got to release all that energy. Each spectral line has a specific wavelength and is for one electron transition to a lower energy level. But now what's kind of interesting is that, like if you look back at this spectrum for hydrogen, we said, you know, here's hydrogen in there, and it had like kind of a orangey red band and a teal and a blue and a violet. Or here on this picture, we kind of see that all the colors together might look kind of pink or purple, but then when I separate that light with a prism, I see the specific bands of color. Well, sometimes the electron is doing different things. Hydrogen is kind of a goofy little guy because there's only one electron, and so sometimes that one electron makes a low energy transition, and sometimes it only jumps like one energy level. Well, then I'll release low energy colors. That's like the reds and the oranges. It's like if I were looking at like the rainbow up here, maybe we should mark in that like the reds and the oranges. This is low energy. Those are lower energy colors. And so if that one electron just gained a small amount of energy, then he'll release a small amount of energy. To us, it might look like then visible red light. Sometimes that one electron gains a lot of energy. If he gains a higher amount of energy, then in order to go back down to the ground state, that one electron has to emit a higher amount of energy. To us, it might look like a higher energy color, and that would be like your blues and violets. So maybe up here we should write high energy. So it's kind of crazy, is that like we can't see electrons. Not even with the most sophisticated microscopes, you can't see electrons. We just have to look at evidence, like from lab data and experiments, and put together models that seem to explain the observations we're getting from the lab. And maybe over time our models still need to be tweaked. I mean, all of this is still, even today, referred to as atomic theory. And 5-10 years from now, there could be more specific tweaks that we could make to these models to make them more accurate when new information is discovered. And so one thing that we should mention too is that when I go back to this picture, they're showing like, I don't know, in this first picture they're kind of showing like 1, 2, 3 energy levels. Well, there's more than 3. There's up to 7 energy levels with the elements that we know of today. They're just not showing them all in this picture. And so it is possible for this little hydrogen electron to just maybe jump from level 1 to level 2. And then if I fall back down to level 2, that was a pretty low energy transition. So I'll release a low energy color. If that one electron jumped from level 1 to level 7 and then falls back down, well, that was a big energy jump. So that electron is going to have to gain a high amount of energy and then release a high amount of energy. That might be when I see a higher energy color, like the purples or blues. Interesting, right? So we have a cross-cutting concept, matter and energy. Each color of light has a specific amount of energy. So if you think about the Roy G. Biv, the reds are low energy, the blues and violets are higher energy. And there are energies beyond the visible light spectrum, and they are emitted sometimes in the lab too. It's just that in our particular situation, it'll be hard to study. We're not going to be able to study ultraviolet light with the spectrum tubes and the prisms that we have available. A hydrogen atom will absorb and emit kind of a red light. There's kind of that bluish, green, teal color. There's a blue and a violet. But there's no yellow or orange. And so like if we kind of go backwards again, either to this picture, here was in the middle the spectrum, the emission spectrum for hydrogen, or kind of the picture of it coming out of the tube, light coming out of this tube. And I'll show you some of these emission tubes. But there is no yellow, or I guess kind of orange, if we say that last one is reddish. And so they want us to maybe explain, like, why aren't we getting any yellow or orange? And it must just be that electrons are not gaining those amounts of energy and then they're not releasing those amounts of energy. So they not releasing energy with those frequencies, wavelengths. Whoa, hello, spell those. I'll say wavelengths. And the only way we know is just by trying this in the lab. That you can go in the lab and electrocute a sample of a particular element, see what kind of light it gives off. If you run that light through a prism, you'll see the visible light spectrum. And if you don't see a particular color, then that atom's electrons just are not making those transitions. Interesting, isn't it? So it's a different way of looking at atoms. Like, you know that there are these rings or energy levels, and that's where the electrons are found. But maybe in a former life you didn't talk about how the electrons can move up and down the energy levels by gaining or releasing specific amounts of energy. Aha! And so here again are these Bohr models. And I bet these pictures down at the bottom with the hydrogen, helium, oxygen, neon, I bet that's kind of looking familiar to you. Okay, yeah, that's what we drew in biology, physical science, middle school, whatever. And maybe in a former science class they told you that like the first energy level holds 2 electrons. So can you kind of see down here, like with hydrogen and helium, they've got 1 electron in the first energy level, and then helium's got 2 electrons in the first energy level. Now, did you ever ask your science teachers why? Why can I only put 2 gumdrops in the first level? Because I really like gumdrops, and I feel like I could fit more in there, M&Ms or whatever kind of models you maybe made when you were in elementary or middle school. Did you ever ask why only 2? Or did anybody tell you, like, once you get up to the second energy level, you can have 8? It's like if you look at neon, neon seems to have 2 little blue electrons in the first ring, and then 2, 4, 6, 8 in the second ring, or the second energy level. Did you ever ask why? Why 8? Who says 8? Why can't I put 10? What happens if I put 9? Why not 7? Well, that's what we got to clean up a little bit going forward. The Bohr model is not all bad. It helps us just to have a nice, simple model of the atom. We know how many electrons. We know what energy levels are, like what distances they are from the nucleus. Is this an electron that's close to the nucleus, or is it far from the nucleus? It helps us to understand, like, energy of the electron, because I bet you've probably been told that, like, the energy levels closest to the nucleus are low energy. So the innermost orbit or innermost energy level is the lowest energy level. And then moving away from the nucleus, the energy level increases. And again, like, low energy is very stable. So electrons in that first energy level are usually said to be more stable than energy levels out in like the 6th or the 7th energy level. They're getting pretty far from the nucleus, and that's going to be unstable when they're out at these high energy levels. Okay, so the Bohr model's not all bad. It shows me the energy level of a particular electron. Is it close to the nucleus, far from the nucleus? And they do kind of show, like, how many electrons are in these rings or orbits or whatever you want to call them. But there's definitely some work to be done going forward. Specifically, like, Bohr models are flat. It makes us picture electrons just flying around in a ring. And last time I checked, matter is not all flat. And atoms are 3-dimensional spheres. And so eventually we want to just kind of clean this up a little bit and make it a little bit more true to other experiences that we have with matter. That how do I take this model and make it 3-dimensional? Like, do electrons really just fly around in orbits? Like, they just orbit the nucleus in a 2-dimensional path? Probably not. So there are some great things about Bohr models, but it's something that we'll revisit going forward. Okay, so question 23, looking at patterns. A fluorine atom has 9 electrons. Draw the Bohr model for fluorine using the pattern you observe for the Bohr models for hydrogen, helium, oxygen, neon. So that's these guys down at the bottom here. Get rid of this now. Whoa, not that much. Get back here. There. Okay, so we got these 4 models down at the bottom. And we're going to try to put in a model of, let's see, fluorine it was. Okay, so fluorine has 9 electrons. I erased part of that. It's fine. Fluorine has 9 electrons. And so it looks here like I've got oxygen with a total of 1, 2, 3, 4, 5, 6, 7, 8. And then neon with a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now Bohr models really are most concerned with the electron structure, so you may not see the nucleus complete with like the protons and the neutrons. So for now, I'm fine kind of following suit, and we'll just put a little F in the middle for fluorine. These models seem to have 2 energy levels. So maybe we could put 2 energy levels in there. And then let's start giving them some electrons. So if I kind of follow, obviously fluorine is going to have 9 electrons and it'll be right in the middle. So it looks like these models have like 2 electrons in the first energy level. And then the second energy level, they kind of pair them. I wonder why. Did you ever ask that? I bet in other science classes you kind of paired your electrons, or sometimes you call these like dot structures maybe, where you pair them. I wonder why. There must be a reason for that. Maybe we'll learn about it sometime soon, right? So let's kind of follow suit. Here's the oxygen, and then it's got 2 like this. And then the oxygen has 1 on the bottom and 1 on the side. Well, if fluorine needs 1 more electron, and if I kind of look at the difference between oxygen and neon, in neon it's like 4 groups of 2, 2, 3, 4. Maybe we could just go and like pair one of these. Get that out of there. Like maybe, I don't know, it could be any of them. What if I did something like that? Or you could have paired like this guy on the right hand side too, and then left the one on the bottom single. That wouldn't have mattered. But here would be a good representation of 2, 4, 6, 7, 8, 9 electrons. The Bohr model of fluorine. This is really getting interesting now, isn't it? Okay, so we're going to do some kind of labs, and we would have finally started doing labs in class, and it would have been fantastic. And so we'll do the best we can, but I'm going to show you some labs where we'll look at real samples of elements, and we can look at the different types of energy they give off and the different colors of energy that they give off. Because now that makes me want to go back to my original model of fireworks. And so at the beginning we looked at some colored pictures of fireworks, and they're red and they're green. And I think maybe that were some of the more prominent colors at the original picture, like at the beginning of the book. It says to compare and contrast the colors and wavelengths of the light emitted from 2 different colors of fireworks based on the elements they contain. Explain why these elements have different atomic emission spectra. This is getting interesting. Okay, so let's pick red and green. So red and green. Okay, if I think about my Roy G. Biv, now I don't know if indigo is really official anymore, or if it's Roy G. Biv. Poor indigo. But remember, like my reds are low energy colors, and my blues and violets are higher energy colors. And so if we kind of mark that in, so the red is low energy, and the violet is high energy. And then to correspond, like the red wavelength would be a lower wavelength. I should say it's a higher wavelength, lower frequency. High wavelength, low frequency. Oh yeah, because if the waves are longer, then it just is that I can't get as many waves in a particular unit of time. Whereas my higher energy colors, oh yeah, distance from peak to peak or trough to trough, this is going to be a low wavelength. Higher frequency. Okay, cool. So they're asking me here to compare and contrast the colors and wavelengths of the light emitted from two different colors of fireworks. And so we could say something like the red light. A red light would be a lower energy. We could say that it would be a higher, maybe we say wavelength, or a lower frequency. The green light would be higher energy. When they talk about wavelength, so it would be a lower wavelength. Ah, interesting. Explain why these elements have different atomic emission spectra. And so again, what would be interesting is that, let's say I see red light or I see green light. If I run that light through a prism, it'll separate into specific bands of color. Now with the red light, it might separate into a lot of reds and oranges and yellows, and the green might have like a lot of green bands, but it might also have a little bit of yellow, or it could have a little bit of blue. And I see a green color because it's a mixture of all those individual wavelengths. Well, if these are the colors that we see, it must mean that that's like the strongest bands in the spectrum. That there must be a lot of red light in the spectrum, a lot of colors in that visible red part of the emission spectrum, or that the green, there's probably going to be some prominent green bands in the emission spectrum of that particular element. Now this is really getting you thinking about fireworks, right? And the different colors of light, and maybe the fact that they're coming from different elements, and it might have something to do with the energy then that's emitted from the fireworks that's exciting the electrons in those atoms, and maybe then it's kind of giving us the different frequencies and wavelengths and energy levels of color. Oh, this is getting so good. But that's enough. This is really long. You probably listened to this on like quadruple speed. I'll shut her down, and then we'll move on.